All right, everybody, welcome back. In this video, we are going to be looking at information from section 5.3 of AP Calculus, determining intervals on which a function is increasing or decreasing. We start here with the definition of what it means to be an increasing function or a decreasing function, although I'm sure most of you have at least a pretty strong intuitive idea of what it means for something to be increasing or decreasing. But it says here, let f be a function defined on an interval I, and let x sub 1 and x sub 2 be any 2 points in that interval I. So, we've got this function defined on the interval I. If I've got these 2 points, x sub 1 and x sub 2, I'll put x sub 1 and x sub 2 on this graph a while as well. Then the function is increasing if, and notice for both of these I said, let's let x sub 1 be smaller than x sub 2. It's increasing if f of x sub 1 is smaller than f of x sub 2, and you can see the increasing function, and that's how we notate that mathematically. And over here on this one, it is decreasing on an interval when f of x sub 1 is greater than f of x sub 2. All right, so that's what it looks like and what it means for something to be increasing, decreasing from a mathematical standpoint. Next piece of theory, this is a corollary to the mean value theorem. We're not going to give it a specific name. We're just going to say, hey, this is a corollary to the mean value theorem. Related to increasing and decreasing functions. So if we have a function that's continuous on the closed interval from a to b and differentiable on the open interval from a to b, again, that's the same hypothesis that we use for the mean value theorem. If the derivative of f is greater than 0 at each point on the interval from a to b, then the function increases on that interval. And if f prime is less than 0 at each point of the interval from a to b, then f decreases on the interval from a to b. Now, at first glance, you might be like, well, I'm not even sure how that's related to the mean value theorem. But this is a direct result of the mean value theorem, and we'll talk about why here. How is this related? Suppose we have a function such that f prime of x is greater than 0. So we're looking at case 1 here. The mean value theorem guarantees that in that case, for all values of c in the interval, f prime of c is greater than 0. Since the function's derivative is always greater than 0, the derivative at any individual point is greater than 0. Since f prime of c is equal to f of b minus f of a all over b minus a, that's your conclusion of your mean value theorem, and since f prime of c is greater than 0, we know that this is positive, that means that this side of the equation must also be positive. All right, and we're looking at the interval from a to b, which means b is greater than a, which implies that this quantity in the denominator is also positive. And the only way that we can take this fraction f of b minus f of a and divide it by b minus a and get a positive result is if the numerator is also positive. Okay, so that means that f of b minus f of a must also be greater than 0, which implies that f of b has to be greater than f of a, and therefore, by our definition of increasing functions, that means our function must be increasing. All right, it's similar if we try to make the argument for when the function's decreasing, except now in that case f prime of c would be negative, which implies that the numerator of f of b minus f of a all over b minus a is negative, and therefore the function is decreasing. All right, let's keep rolling on. Here's our step-by-step approach that we are going to take for determining when a particular function f of x is increasing or decreasing. First thing we're going to do, find the derivative of the function f prime of x. There are some situations where we might already be given the derivative, but if we're given the function, then we first need to find the derivative. We're going to draw a number line, and we're going to label it f prime. All right, and when we're done doing that, we're going to have what we refer to frequently as a sign chart. Sign charts are a very helpful tool that we can use on our AP exam, although they are not standalone justification for your statement. Basically, you'll use a sign chart to gather information, and then you'll have to collate that information and express it in order to get credit for your understanding of the concept. We'll talk about that a whole lot more as we work through examples throughout this unit. The next thing we're going to do is we're going to find the critical points of the function. We talked about finding critical points in the last lesson, and the way we're going to find those is we're going to find where f prime of x is equal to 0, or where f prime of x is undefined, and those will be our critical points. Then we're going to mark the locations of those critical point zeros, and also the undefines, on the number line that we drew from step 2. Notice I say in here in parentheses, they don't need to be perfectly placed, but they do need to be in order from left to right. It's okay if the space between 1 and 2 on your sign chart is the same as the space between 2 and 5, because what we're really focusing on is what happens on the intervals in between those two numbers. We're not worried about our number line, our sign chart being drawn to scale. Then what we're going to do, once we have our intervals established, we're going to test points in each of the intervals by substituting the nx value from that interval into the derivative and determining if the value is positive or negative. Again, we don't really care about the value, we only care about the sign. There's no difference for us fundamentally between whether the derivative is 2 or whether it's 2.5, because in both of those situations the derivative is positive. And then for each point that we test, we're going to place the appropriate sign above the corresponding interval on our sign chart. And then we are going to identify the intervals where the function's increasing or decreasing and justify our answer by making a statement connecting the intervals to the sign of the derivative. And you'll see this a whole lot more. And notice I mentioned this earlier, while it's a great tool for analysis of a problem, it's not considered sufficient justification on your AP exam. Okay, so let's get down to brass tacks, and we'll work through this step-by-step approach in our first example from this lesson. Example 1. Determine the intervals where f of x is equal to 2x cubed plus 3x squared minus 36x plus 18 is increasing and decreasing. Justify your answers. So the first thing I need is I need the derivative. I'm not given the derivative in this problem, so I'm going to actually have to take the derivative of f of x. So I'm going to have f prime of x is equal to, and I take the derivative, we've got 6x squared plus 6x minus 36 as our derivative. So there's our first step. We've found the derivative of the function. The next thing I'm going to do is I'm going to make a number line, and I'm going to label it f prime of x. This is going to be our sign chart that we use to analyze the behavior of the derivative. So we're through our first 2 steps of our process. The next thing I'm going to do is I'm going to determine where the derivative is equal to 0. So I'm going to set f prime of x equal to 0. And now I need to solve this equation, and I can do that however you see fit. I can use a quadratic formula. If I have a calculator handy, I can use my calculator to solve the equation. I'm not going to take the time to do that. I'm going to just go ahead and factor this because I know it's factorable. That's what happens when you make the problems, is you know for sure whether they're factorable or not. This one factors as such, and therefore the critical locations for us are at x equals -3 and x equals +2. Okay? So now we're done with step 3. We've found everywhere where f prime of x is equal to 0 or undefined. Notice this is a polynomial, so we weren't worried at all about it being undefined, and so we didn't need to really concern ourselves with that calculation. All right, now I'm going to mark these locations on my number line. I have 2 critical points, so I'm going to put 2 marks on my number line, and -3 is smaller than 2, so I'm going to put -3 to the left and 2 to the right. All right, that's step 4. And I usually also like to mark above these points whether the derivative is 0 or undefined there. You don't necessarily have to do that, but I feel like it's a good idea for us, especially when we're running into things that are a little weird. It helps sometimes if we know that that's a place where the derivative is 0 or undefined. All right, now what I need to do is I need to take points that are in this in each of these intervals and test whether or not the derivative is positive. And I'm going to actually use, here where we solved and found where the derivative was equal to 0, if I divide this last equation by 6, 0 divided by 6 is just 0, this derivative fundamentally for our purposes in calculation is fundamentally equivalent to this. So I can test the sign of this derivative in various intervals by just substituting values into these expressions. And that's one of the easiest ways we can do this. So first let's do the interval to the left of -3. So I'm going to pick a number that's smaller than -3. Doesn't matter which one I pick, I'll pick -5. And I'm going to imagine what happens when I substitute -5 into this factor. What happens when I substitute -5 into this factor? And I'm not going to do any calculations here. I'm just going to concern myself with the signs. And factored forms work particularly well for me to do this. If I substitute -5 into this factor, the result is negative. If I substitute -5 into this factor, the result is also negative. I've got one factor negative, another factor negative. The product of those two factors is going to be positive, which means that the derivative is positive in that interval. Then I go into the middle, and I'm going to pick a number between -3 and 2. I'll pick 0. I substitute 0 into this factor. 0 plus 3 is positive. 0 minus 2 is negative. Positive times a negative means that this is negative. And as we go by, that's the beauty of separating and partitioning off these intervals, is if I have them partitioned correctly, I know that if I find that the derivative is negative for one value in this interval, that means that it's negative for all values in that interval. That's why these work so well for us. And then the last interval, I want to pick a number bigger than 2. I'll pick 3. If I substitute 3 in here, it's positive. If I substitute 3 in here, it's also positive. A positive times a positive is a positive. So this interval is positive. It's important for me to say at this moment in time, don't assume that the intervals here alternate positive and negative. If they did, we'd have really no need for this sign chart, but they don't always do that. And so it's important for us to actually identify the positivity or negativity of the derivative in every one of these intervals. All right, last thing I need to do is I'm going to identify where the function's increasing or decreasing and justify my answer by making a statement connecting the intervals to the sign of the derivative. So I'm going to say f of x is increasing. I'm going to do increasing first. Is increasing on, and I look at my sign chart and I see where the derivative is positive, because positive derivative implies increasing function. So it's increasing from -infinity to -3, union 2 to infinity. And my reason is because f prime of x is greater than 0. And then I'm going to do decreasing, since we wanted to identify where it was increasing and decreasing. We're going to say f of x is decreasing on the interval, and my interval is where the sign chart shows negative. That's from -3 to 2. And my reason statement is because f prime of x is less than 0. All right, and there's my answer to where this function is increasing or decreasing, with my answers justified. All right, we're just about out of time for this video, so we're going to call it quits right here. Come back and join me next time, where we'll work through a couple more examples applying this process to identifying where functions are increasing and decreasing. All right, have a great rest of your day, everybody, and we'll see you next time.